The problem introduction. The Tower of Hanoi is a classical mathematical puzzle with 3 pegs and a number of disks. All disks start on a source peg stacked in decreasing size, largest at the bottom. The goal is to move the stack to the destination peg using the auxiliary peg. Following these rules, the rules were only one disk can be moved at a time, only the top disk of a peg can be moved, and a larger disk cannot be placed. And this is the this includes the introduction part. This was the initial setup, objective, and the rules. The rules, as we have discussed, only the topmost disk on the peg can be moved, and the larger disk may never be placed on the top of the smaller disk. And coming to the state space representation, to analyze the problem, use the state space representation. Each state configuration of disks of on the 3 rods. Example for 3 disks ABC, where each symbol shows which disks are on the rod, and each transition moving a single disk legally. This state space grows exponentially with n. For 3 disks, we can easily draw the state graph, but as the value of the n increases, the state space diagram also increases. And the algorithms I have used for solving the Tower of Hanoi was, there were mainly 2 approaches I've used here. One was depth first search, and I used a recursive manner. The classical recursive solution, steps for n disks: move n-1 disk from source to auxiliary, and move the nth disk from source to destination, then move the n- disk from auxiliary to destination. So here the base case was only when only one disk remains. That's the base case here. And always produce the optimal solution within 2 power n-1 moves. And the other algorithm I have used was best first search. It's a heuristic based approach. Here use the Tower of Hanoi as a search problem. It uses the priority queue and a heuristic function. Heuristic in the sense how many disks are not at on the destination rod. It tries to expand the state that looks closest to the goal. It's more flexible but heavily depends on the heuristic quality. And coming to the performance of these algorithms, for the DFS it moves in 2 power n-1 ways. The time complexity was 2 power n. Space complexity was O power n, as it's a recursion stack, and works efficiently even for the larger n because it goes by a depth. Coming to the best first search, here the moves depend on the heuristic. It may or may not be optimal, and the time complexity was O of b power d. That means branching factor into depth. Space complexity was exponential, stores many states. And the ideal solution, the ideal thing for best first search was it only works for the small values of n. Beyond that, the memory blows up. And coming to the advantages and disadvantages. For the DFS advantages, it's a very fast for the classical problem. It takes minimal memory and always optimal solution. Thus disadvantages were it's not flexible for puzzle variations, and deep recursion can cause stack overflow if n value is very large. And for best first search, advantages were it can handle modified versions of the puzzle. It's flexible with custom heuristics, and it's useful in research or AI contexts. And disadvantages were it uses very high memory and CPU uses. It's very impractical for the larger values of n, and it's harder to implement compared to the DFS. And coming to the visual comparison, let's say for n equal to 3, DFS path always gives the same 7 optimal moves. It's a predictable one. For the best first search, depends on heuristic. With a good heuristic, you can find same optimal path, but takes different exploration strategy. Coming to the summary and recommendations. For classical Tower of Hanoi, always use DFS, recursive solution. For modified puzzles or research, best first search is useful because of its adaptability. Key takeaway. And DFS is best for standard problem, but best first search for best for complex or custom variants. Let me show the code here. I will run this. I'm going to run this. We can see it asks for the number of disks. Let's say we give the n value as 3, and it gives the each of the possible solutions for both of the things, for DFS and best first search. Okay, now let me explain the code here. So the program demonstrate basically this code demonstrates 2 different approaches of solving the Tower of Hanoi problem. One was DFS and one was best first search with heuristic based strategy. And let's come to the implementation of Tower of Hanoi. This function you can see here, Tower of Hanoi DFS. This function is a standard recursive of Hanoi solution. We have if we have n disks, the logic is move n minus 1 disks from the source rod to the auxiliary rod, and move the largest disk, that means the nth disk, from source to the target. Then move n minus 1 disk from auxiliary to the target. Let's say, for example, if n equal to 3, the recursive calls breaks the problem into smaller sub problems with only one disk is left. So the part prints. So this part prints the exact sequence of the moves required to solve the Tower of Hanoi optimally using recursion. And let's say here we are solving the problem as state space search. Here each state keeps track of the rods where each disk currently is, and the list of moves taken for the to reach this state. This that is what we're discussing now. And the cost, how many moves we have done, and the heuristic, how many disks are still not in the destination rod. And coming to the heuristic function, 1 minute. This is the heuristic function. This heuristic here is a simple, it generally counts how many disks are not yet in the destination rod. If n disks are on the rod, see heuristic 0, that means goal reached. And we are using priority queue here. And here the states are explored based on the cost plus heuristic. This ensures we always expand the state that looks closest to the goal. And for generating the next states, this is the main part that we are using here. So basically what it does was, for each rod we try to move the top disk to the another rod, and we check the Tower of Hanoi rules. Cannot place a larger disk on the smaller one. So each valid move creates a new state with updated rods and the moves. And this push this new state into the priority queue with updated cost plus heuristic. And finally we need to check the goal rate, goal check. Here is the goal check. So for this goal check, so when heuristic equals to 0, all disks are on the destination rod. So here the solution is found. So print the sequence of the moves. And this is the main function here, just to give everything. Takes the number of disks as the inputs. These are the inputs that we're going to take. One is for the DFS and one is for the best first search. So key differences here: DFS always gives the optimal solution, and it's a very structured and predictable. BFS, best first search, explores the problem as a graph search. Uses heuristic to guide towards the goal. It may explore multiple states, but still eventually finds the correct sequence, but it is not good for the larger values of n. Thank you.